Everybody hear me okay? So in conclusion, thank you for your attendance. And Keith and I are going to present some data that the Iowa Soybean Association collected in Lyons Creek. And so you might be thinking, great, more information about nitrate and tiles. But this is a really interesting data set, and we felt was worth sharing today. So we hope you agree. I'm going to start with just a little bit of background, talk about the data collection and the data analysis. This is for calendar years 2009 through 2013. And then at that point, I'm going to hand it off to Keith, and he's going to talk about a paired watershed approach and how that might work in this watershed. And this idea of a minimum detectable change. Based on the water quality that we've seen already, what kind of change would we have to bring about through practices in order to be able to see it or to give it any sort of statistical meaning? So the upper right-hand insert there shows the Lyons Creek watershed outlined in red, and then 3 tile drain catchments or sub-watersheds. Actually, you could think of them as drainage districts. That's where we are looking at the information here. Tile drains labeled 3T, 4T, and 5T. And then for some broader scale context, we've also looked at some information in the Boone River south of Webster City, both the DNR's ambient monitoring location, as well as some collection by the Iowa Soybean Association. This is pretty much what a typical tile drain outlet looks like in Lyons Creek. Very small tiles that discharge for a short distance through a headwater tributary or a ditch before entering Lyons Creek directly. Lyons Creek is about 11,200 acres, somewhere in that vicinity. In the Boone River watershed, of course, the drainage area is many times greater, 900 square miles. Again, this is some distance downstream of Webster City, whereas Lyons Creek enters the Boone River in Webster City itself. A lot of information on this table here, I realize, but the main point here is that these 3 tile-drained watersheds that we've looked at are remarkably similar. The only things that are really different at all are the size, about 640 to 2,700 acres in size. The soil texture is quite similar. The topography is very similar. Tile drainage that we would expect to see there is very similar. We don't really know where that is for sure, but what we'd expect to see as having tile drains. Very similar across the watersheds. The one difference would be the areas that we would expect to see manure application. This is based simply on the location of animal feeding operations, kind of working outward from those where there are row crop areas where that manure would likely be applied. So you can see there that 4T actually receives the least amount of manure, which you might find interesting later on. So the results, I'll just jump right in here. This is time series information. Each point you see is a monthly average in terms of either precipitation in blue or water yield from the tiles in red, and then the green line there is water yield or flow in the Boone River. The highlighted columns there, that represents that peak season of April through July. And you'll notice that the Lyons Creek tiles and the Boone River water yields are tracking each other as we'd expect. But you'll also might notice that the water yields don't necessarily track the rainfall. So it's not just rainfall over the long term that's important, but it's the timing that's very important. Same kind of information here. This is actually, though, nitrate concentration, flow-weighted average concentration by month. And you'll see that, again, the April to July time period is where things start to spike up. You'll notice in 2003 it shot up and then it stayed up. But this was a very low flow period, the second half of 2003, so that's not that significant in terms of load, as you'll see in the next slide. But it's interesting that the concentrations did stay up, and I believe they saw the same kind of behavior in 2014. If somebody of the Soybean Association is here, they can verify that later. And then the product of the previous 2 slides, flow and concentration, give us our nitrate loss or nitrate yield through the tile drains. We looked at the distribution of flows coming from the tile drains, each of the tile drains in the Boone River. The Boone River there is the black line, and then each of the tiles. And more importantly than that, we looked at when was the nitrate actually moving in this system. And what we found was pretty interesting. Nearly 60% of the nitrate that comes through the system moves during the highest 10% of daily flows. Similarly, the highest 25% of flows is moving about 85% of the nitrate export. And the top half of flows essentially is moving everything. Another plot with a lot of information on it. So we'll just walk through it and I'll point out a couple things. The dotted black line on top, typically, that's the annual cumulative precipitation. And then the dashed lines are the annual cumulative water yields from each of the 3 tile drains. 3T in blue, 4T in red, and 5T in green. And a couple things that jump out right away is, first of all, red always tends to be on top, if you'll notice that, with the exception of 2012 there. That's tile drain 4T, so it had the highest water yields, concentrations, and loads. And then if you look at 2011, 12, and 13, you see an interesting pattern there. Despite pretty similar annual precipitation in those 2 years, we had a real drop because of that extended dry period. The tiles just didn't flow, weren't moving much nitrate. Then in 2013, the water yield jumped back up because of the wet spring, but really not all that different than 2011 and lower, in fact, than 2009. Yet our nitrate losses spiked, and we'll talk more about that as well. Some of the early implications of this information is that this confirms that nitrate loss is primarily a hydrologic-driven event. The strategies need to work during wetter than average conditions. Having said that, hydrology certainly doesn't always explain some of the variation or the deviation that we would expect. Also, the patterns downstream in the Boone and likely beyond very much mimics the patterns in the tiles. So this really is the scale we need to be working at to get the most efficient reductions in nitrate. This is actually 2014 information. Every circle on this graph represents a tile drain sample collected by the Soybean Association around the state, wherever they're monitoring. The red dots represent the Lyons Creek. So Lyons Creek, for the most part, represents that variation amongst the state. It's maybe a little bit higher overall. I would say it certainly is. But what's really interesting is tile drain 4T represents almost every single maximum concentration. So there's something special about 4T. We're certainly not necessarily pointing at bad actors or over application or anything. It could just be something that's inherent about that system, the soils and the nitrogen dynamics in the soil there. Who knows? There could be a lot of things. But it is an opportunity certainly to make some gains in the reduction of nitrate loss. This is a summary that really shows everything. I know that's a lot of numbers as well, so I've kind of directed your attention to a few things here. First of all, just the variation across tiles, but also year to year. Exports from 3 pounds per acre per year all the way up to 93. If you are used to scientific units, that's well over 100 kilograms per hectare in 2013 coming off of that. That's pretty hot. 5-year average was about 36 pounds per acre per year, or 40 kilograms per hectare per year. That's above what we would expect to see in most of the literature, especially at this scale, which is beyond a field plot scale. The average nitrate concentration was about 18 to 18.5 milligrams per liter. I want to put some of this in a little bit of context. I think as water quality professionals that might not be agronomists, we tend to think of the leaky tiles as the biggest loss of nitrogen from the system. This is just a real simple exercise, an oversimplification, but illustrates that we kind of forget about the crops. And Chris Anderson in his talk yesterday alluded to this as well, but far more of the nitrogen is actually exported from the system by the harvest of crops. That's a good thing. Typically, if you assume this assumes countywide yield data. We didn't have watershed-specific yield information. But if you use the county-wide yield data and assume that represents, or Lyons Creek represents that fairly well, and a 50-50 corn to soybean ratio, you can come up with about 120 pounds per acre per year that's typically removed with the harvest. That's the green lines. And then on top of that shows how much was lost through the tiles as per our observed information, observed data. The average total is about 155 pounds per acre per year. Notice that dip again in 2012 because of the drought. We've got not only very low nitrate loss in the tiles, but a lower harvest yield as well. That just simply carried over to the next year when it got wet in the spring of 2013. It pretty much just made up the difference. What's interesting is that yields in 2013 countywide were pretty low as well, so that probably maybe translated to some of the higher concentrations we saw in 2014. Of course, the flows weren't as great. This shows kind of the same thing, but extends it throughout the 5-year period. The bottom axis here represents the prior year's yield in bushels per acre for both corn in blue and soybeans in red. And then on the y-axis is the nitrate loss through the tile drains in pounds per acre the following year, and it's really a strong relationship. There's some circular argument going on within these relationships, but it just really does illustrate that yield doesn't have to compete with less nitrate coming through the tiles, but it is certainly something that needs to be managed, and Mother Nature kind of gets in the way of that management. I haven't talked about nitrate fertilizer or nitrogen fertilizer application, and it's kind of a touchy subject. I hesitate to put this up here because sometimes it's misunderstood or maybe leads people to draw some conclusions that might not quite be appropriate. But this was a relationship first developed by Lawler and others. I know Matt Helmers was on that work as well. And then it was utilized in the nutrient reduction strategy. And really it just demonstrates there is a relationship between the application rate and the tile drain nitrate concentration. Certainly there's quite a bit of variation around that line as well. But if we look at the Lyons Creek concentrations, which is about 18 or so, it would imply that we have application rates, if this relationship holds at this scale, of about 190 pounds per acre, or maybe just over 200 kilograms per hectare nitrogen application. That would be about what we would expect in this region of the state. So it looks like that relationship might hold. So in summary, before I hand it off to Keith, the main things we walked away with is maybe nothing really all that surprising. The patterns downstream certainly follow the patterns in these tile-drained watersheds. Water yield is the primary driver of this nitrate loss, not necessarily rainfall. Timing is very important and muddies that relationship up. The highest 10% of flows move almost 60% of the nitrate. The highest half of flows move essentially all of it. But the nitrogen supply can also be very important. And that is affected by crop yields, as we've already talked about, fertilizer application, not just the rate, but the source, the type, the timing, the method that it was applied. And then, of course, the inherent soil properties, the organic matter, how fast are the mineralization rates or the immobilization rates. So there's a lot that complicates that picture. And then finally, we did observe some pretty significant differences between tiles, even though they're in the same Huck 12 watershed in close proximity to one another and have pretty similar characteristics. So we can explain that variation, and if you can imagine if you're trying to model or simulate how these systems work, if we can't even explain the variation in the observed data, we have a really hard time trying to predict the behavior of these systems. Could be agronomic differences going on here, or the tile drains themselves remain a bit of a mystery at times. We don't know exactly where they are and where they aren't, what the spacing is, what the depth is relative to the groundwater table, all of that kind of thing. But because we can't explain that difference, that variation, it doesn't mean we can't take advantage of it, and that's what Keith's going to talk about next. Pardon us while we do the hand up here. Just put that and then you can
Okay. I'll just try and use the microphone. Can you hear this okay? Some nod way up there? Yes, okay. Taking the baton from Charles, the idea is that, like he said, that we may not be able to account for all the differences in these tile drain watersheds, but we can use this information towards implementation of something like the nutrient reduction strategy to figure out and test for the effects of conservation practices. The objective of what my portion of the study would be essentially is to say, what's the suitability of using these large or these drainage district size basins in a paired watershed analysis? Now, we haven't quite actually implemented this, but this is the analysis to say how suitable are they to this type of analysis, because this really is an approach that works very well for testing the effects of conservation practices. So one of the things that we looked at was, here we have these three drainage districts side by side by side. How paired are they? Okay, so a concept that we kind of developed here was just an idea of, all right, given more and more samples collected, what is the intrinsic variability between these samples? So do they, usually the common rule of thumb is that the more samples you collect, the greater the similarity and the greater ability you have to pair them up. Well, in this analysis, and this goes from a year short of Charles's work, so this goes from 2009 to 2012. Interestingly enough, the more samples we collected during this time, the worse the correlation between them that we observed. Now, this is kind of counterintuitive and really troublesome in terms of a paired watershed study, because you want to develop a good calibration relationship before you test for significant differences. So in this case, the standard deviations between different pairs increased with additional sample collection. Same thing with the cumulative correlation. So with more and more data collected, do they become more or less correlated with time? And unfortunately, in this case, it varied quite a bit, although some pairs were much better correlated than others. So if you look at the correlation coefficients between these different tile drainage sheds, for the total period, the correlation between 3T and 4T was only 0.4. Okay. On the other hand, the correlation between 4T and 5T was 0.8. Okay, much better. You know, we're still trying to figure out why, but that's just what the data shows. And follow along what Charles said in terms of the time when the tiles are actually flowing and moving, the correlation among all the samples got a lot better. So if we focused on the March to July period, the correlation between these different pairs improved remarkably to 0.8 for the 3T, 4T, and 0.93. So that gives you some ideas that maybe we need to work on a paired watershed for drainage districts or tile drainage focused on the time that they're actually flowing and are supposed to be working. And finally, a little analysis here was just a regression between different pairs, and what you really see is the difference between the entire time period and versus the March to July time period, where the regression between the two different drainage district pairs improved significantly during March to July. Okay, so I think I've built the case that there can be pairing going on to say if we're going to test for conservation practice effectiveness, these may be suitable for paired watershed design. All right, so the next focus is, all right, if there's going to be a paired watershed design, what's the idea of how much change are we going to have to implement based on the monitoring record we've developed so far? How much change do we have to make in terms of the watershed nutrient delivery to be able to see a significant differences when these practices are applied? And that's the idea behind this minimum detectable change, which is the change needed to discern a significant difference before and after BMP implementation. So in the vast majority of watershed projects, there's really no investment made in gathering this pre-BMP calibration period data. What we have here is, in this case, 4 years of pre-BMP data to use it to say what kind of change are we going to have to make to see an effect. It's a function of the number of observations you make and then the variance among those observations. So the more data you get, the closer the narrower the variance gets, you can detect changes in the future a lot better. So we use this MDC concept in two different ways. We assumed what happens in a balanced design. So we collected, 2 samples a month, bi-weekly samples for 4 years. What if we had that same sample collection, 100 observations over 5 years in the future? And then secondly, how many samples would we have to collect to see a 10% change based on the variability of the data so far? And that's kind of shown in this table. Let's highlight a few things as Charles did. So what we have are the treatment and control pairs, and it matters which one you designated the control, which one is the treatment. So that's in the first column, first 2 columns, and then say the number of observations. Well, the MDC, the minimum detectable change, varies quite a bit. If we used one watershed, 5T is the control, and then we did treatment in 4T, well, the minimum detectable change was 7%. On the other hand, if we switched it around and looked at 3T versus 5T, all of a sudden the minimum detectable change is 13%. We'd have to make, based on a balanced design, we would have to collect 474 samples over 18 years in order to see a significant change, because there's so much variability in the relationship between the two during the calibration period. On the other hand, like I indicated earlier, if we use this concentrated period from March to July, the MDC goes down. Okay, so if we focus on when they're best suitable to being paired, we can get by with fewer samples collected in the future and a greater opportunity to see change in the future. To emphasize the point in a slightly different way, if we look at just how well they're correlated, the difference between a correlation coefficient of 0.4 versus 0.8, given the same number of samples, would suggest that we're looking at big differences in how they're able to measure that change in the future. Okay, we could spend more time on this, but in the interest of time, let's move forward. Charles mentioned a little bit about why the variability between treatment and control pairs, possibly variable fertilizer manure applications, presence of surface intakes, climate variability. We clearly had differences in climate as it affected on nitrate yield and carryover, proximity and size. One basin was larger than the others. All these things need to be factored in, and we haven't figured out all the answers, but again, those are the differences, things that might have contributed to the differences. Finally, let's end with some ideas of how do we use this information? Well, utilizing 5T as the control and 3 and 4T as treatment basins provided the lowest minimum detectable change, okay, an average of 8%. What practices, based on the strategy, are capable of producing an 8% change in concentration? Well, fertilizer reductions are capable, cover crops, treatment of wetlands and bioreactors, and land use change. So it's not like an 8% change in the concentrations is insurmountable. I mean, it's possible based on some of these practices. Some conclusions from this part of the study. Drainage districts and these tile sheds are very amenable to paired watershed analysis, especially if you focus on the time periods where they're actively flowing, okay, March to July. If you have lack of correlation, it's going to affect the ability to detect a change in the future. So it's really important and critical to see how well they're correlated before you invest in the long-term treatment or monitoring for treatment. And suitably, if you get a chance, studies should really consider this relationship before you even decide which one's the treatment and which one's the control, because it really matters on which one is chosen versus the other. And detecting an 8% change is entirely possible in this watershed, given the history of sample collection and possible future. Now, the very last thing I'm going to end with is kind of related, but it's also relevant to the discussion that we have in the Raccoon and elsewhere about drainage district contributions. This was based on only a couple years of work in the Lyons Creek watershed, but it still holds. It's the idea that concentrations essentially scale with basin size. The graph and the box plots on the left, impossible for you to read. Nitrate concentrations on the y-axis, the different site selection on the x-axis. The three drainage districts, as you would expect, show high concentrations, but those concentrations decrease with additional basin scale, okay, in a very regular way. In fact, if we plot those concentrations that from the 3 trial drainage watersheds to Lyons Creek, to the Boone River, to the upper Des Moines and lower Des Moines, they actually plot against the log drainage area, they actually plot as a very straight line, showing that they're scaling in these concentration patterns. Now, the idea of an 8% change in the Lyons Creek basins is doable, but what's the idea of the relationship? If you make a change in these drainage basins, drainage districts at one scale, how does those changes propagate downstream? Well, that's the idea behind this graph, is that if we can reduce the concentrations of nitrate delivered from drainage districts high in the watershed, the changes propagate downstream. So we don't have to achieve necessarily a massive reduction at high in the watershed from the drainage districts. We have to do enough to essentially move the anchor down to a level where we let natural processes of dilution and different land covers and contributions that things take over to reduce these concentrations further downstream. So I think this is actually a good news story for this idea of the relationship between headwater drainage districts and downstream water bodies, is that this scaling relationship suggests that you don't have to make 50% reduction in drainage districts to have an effect downstream. You've got to do a little bit up there and then let nature take its course with the processes downstream. Okay, and that would be the end of our presentation. And,
okay, while we set up, you two can answer questions.
Sure.
Can you leave that, Chuck? Our next speaker.
Any questions?
There samples taken as soon as a mile reaction?
They might be in one of the watersheds. I can't answer that question, but there would be no samples that would be dramatically affected by any bioreactors in the watershed. That's a field scale practice. And these were all small watershed scale monitoring locations. So essentially, no.